Okay, so I'm having to go through and kind of reintroduce some of these because the numbering is getting confusing with the chapters. The problem with like most textbooks with respect to chemistry is that every textbook, like they do the exact same topics, but they just do it in different chapters, right? So it just makes everything super confusing. So right now, I'm assuming that we are using Mastering Chemistry through Pearson. Specifically, the textbook that we are going off of at this point in time is Chemistry. Where's my thing? So Chemistry, a molecular approach. And again, if we're using Mastering Chemistry at this point in time, you do have access to the e-text for this for free, this textbook. And this is by, just as a note, Waldo Tro. So I reference Tro a lot in a lot of these different lectures. Okay, so with that, again, chapter things always change and the numbers that they have them. The topic that I'm going to talk about today, which is termed periodic trends, that is found in chapter 9 of this edition. So this, at this point in time, is also the 5th edition. I should also mention that. So everything I'm talking about with respect to this lecture is dealing with periodic trends, which is technically chapter 9 in Chemistry, a Molecular Approach, 5th edition, okay? So before this whole pandemic thing started, we had been using OpenStax, right? So OpenStax was that free textbook that we could use online. And in OpenStax, if that's what you're still using, that's fine. But OpenStax really condenses a lot of this material. So this is technically Chapter 6 in OpenStax, and Chapter 6 deals not only with what we're talking about today, but also all of that quantum stuff that I talked about in the previous lecture. So Chapter 6 in OpenStax is essentially quantum mechanics, quantum, if I can spell that correctly. So quantum mechanics, as well as electron configuration, and all the stuff that we dealt with that figuration, and then periodic trends at the very end. So it's actually becoming kind of apparent that that OpenStax is really like a glossing over of material, whereas in the Tro book, which I actually really do think this is probably the best textbook out there, he really spends some time actually going over this stuff, which I think I prefer. Okay, so with that said, right, this is where I'm at. This is what we're going to be talking about. I'm just going to kind of briefly introduce the idea behind what you're going to gain from this chapter, right? So with respect to periodic trends, ideally, now that we have this development of quantum mechanics, and now that we have this development of why the periodic table is arranged the way it is, now we can kind of take that a little bit farther, and we can essentially begin to explain or predict behavior of various atoms or various elements just based on their position in the periodic table, right? So that's essentially what periodic trends is going to do. There's going to be a couple of different things that we're going to look at. So atomic radius is one. What is another one? So something called ionization energy, electron affinity, metallic character. These are all things that, given like a list of various elements, a list of various atoms, you can predict all of these things just based on looking at their position in the periodic table. And that's what this entire chapter is essentially going to deal with. So what's good about this chapter is it's more conceptual, and it's not mathematically based at all, so that kind of speeds some things up a little bit. And yeah, if you're not super into math, but you like the concept of chemistry and you understand a lot of the concepts of chemistry, then this chapter tends to do explain things pretty well, I think. So with that, I'm going to go ahead and get started. So what is like a real life situation where periodic trends would be important? So if you guys are taking biology or anatomy and physiology or something like that, you should know that part of the nerve signals that we get in our body are due to the presence of potassium as well as sodium ions, right? So there are little pores that are in our cells that pump sodium out of our cells and potassium in, right? And that's how we essentially transmit these little nerve signals, right? So these pores are specific to sodium and potassium, right? Potassium cannot go in through sodium's pore and vice versa, right? So both of them, sodium and potassium, only have, or they have the exact same charge, right? They're both a +1 charge. So these pores can't differentiate these two atoms or these two ions on the basis of charge, right? Instead, what they differentiate them on is the basis of size. So potassium ends up being a much larger atom than sodium, and so because of that, potassium fits through its pore, whereas sodium doesn't fit through potassium's pore and vice versa. Okay, so this idea behind size, this ion size, or what we're going to call atomic radius of ions and atoms, is part of this periodic trend property, right? We can predict later on or after this chapter that sodium is smaller than potassium just based on their position in the periodic table. Okay, so where does this kind of start off at with respect to periodic table? Well, again, as I mentioned at the end of chapter 6, it all really starts off with Dmitri Mendeleev, right? So he had predicted, or he had noticed, right? So he had noticed when he arranged elements in order of increasing atomic mass that various types of properties began to recur periodically. And so he had stated this as his periodic law. And he had arranged these elements that had similar chemical properties in the exact same column, right? And so that's where we got kind of our basis behind the periodic table. Again, the problem with periodic law is it's great. It can predict, just the basis of the periodic table, but it doesn't actually give us a reason why. It doesn't explain why you do see these recurring properties occur and why the periodic table takes on its shape. Right? So that was periodic law. And so hopefully now, after chapter 6, we know why the periodic table is shaped the way it is, right? It's all because of quantum mechanics and these orbitals that quantum mechanics have given to us with respect to electrons, okay? And so now that we know that, we can kind of start to explain these various similar chemical properties that Mendeleev was noticing with respect to our different groups and our different columns in the periodic table. Okay, so again, quantum mechanics gives us the periodic table in terms of orbitals, right? So the first two columns in the periodic table are what we call the s block elements. They are filling the s orbitals for each given shell, right? The transition metals are the d block elements. There are 10 total columns across because, again, there are 5 d orbitals, and each orbital contains 2 electrons. So that's a total of 10 electrons that can go into those d orbitals. That's why we get 10 columns across in the transition metals. As we move on to the right side, our non-metal part of the periodic table, again, there are 6 columns across because there are 3 p orbitals and 2 electrons can go in each. And again, for the lanthanides and actinides, there are 14 columns across because there are 7 f orbitals, 2 electrons go in each, so there are 14 total electrons in filling the f orbitals, right? So we have blocks now, right? And these blocks go back to these orbitals that quantum mechanics have given us. Okay, so quantum mechanics also explains why elements that lie in the same column or are in the same group with respect to the periodic table, why they display the exact same chemical properties, right? So now we know that those elements, let's say the alkaline earth metals, the alkali metals, all of those guys in the same column have the exact same number of valence electrons. So valence electrons are the electrons that are in the outermost principal energy level for each individual atom. They are held the loosest with respect to the atom, and so because of that, they tend to be the electrons that participate in chemical reactivity as well as bonding. So since every atom in the same column has the exact same type and number of valence electrons, they're all going to kind of behave very similarly when it comes to chemical reactivity and bonding. Okay, so now we're going to kind of reconsider some of these groups that we had talked about previously, some of these columns in the periodic table, in light of the fact that we now kind of have quantum mechanics to help explain their reactivities. So the first one I'm going to start talking about is the noble gases, right? So the noble gases are in the very last column of the periodic table, and we will call this column 8A in our kind of standard nomenclature with respect to the periodic table, okay? So we'd always said, well, noble gases are just happy. They've got, however many electrons, etc. But now we know the reason why, right? So noble gases aren't very reactive because of the fact that their electron configuration is filled, or they have essentially filled in their electron configuration whatever type of shell that they're in, right? So they have all of their s orbitals filled, they have all their p orbitals filled, and so they're extremely happy and extremely stable in that state, right? So they have filled whatever shell that we are dealing with, okay? Because of that, again, they are non-reactive. If they gain electrons, that's actually going to increase their energy, so that's not great. If they lose electrons, that's also going to increase their energy. So the reason why they are so non-reactive is because of the fact that any type of chemical reactivity would actually increase their energy, and we always are wanting to tend it to lowest energy states. So everyone always wants the same exact noble gas electron configuration. So that also helps explain why we see these various types of reactivities for things like the alkali metals and the alkaline earth metals, right? So the alkali metals do not have a noble gas configuration, but if they lose one electron, they will get to the noble gas configuration, right? And so that's why the alkali metals tend to form +1 cations, because again, they have one little tiny valence electron, right? And if they lose that valence electron, they will obtain their noble gas electron configuration, which is nice and stable and what they want to do. And so because of that, all of these guys in group 1A will lose an electron to get to that noble gas configuration. Same thing on the other side of the periodic table for the halogens, right? So these guys, to get to their noble gas or their nearest noble gas electron configuration, just need to gain one electron, right? And so that's what they do chemically. They tend to gain electrons in terms of chemical reactions. And so when they do that, they form this -1 anion, and that's why we see all of the halogens kind of behave very, very, very similarly. Okay, so now we're going to start talking about these periodic trends. And again, the purpose of talking about these periodic trends is being able to utilize the position of an element in the periodic table to help predict some of its chemical and physical properties. So the first trend that we're going to talk about is something called atomic radius. Okay, so atomic radius, there's a lot of different ways to define it, okay? There are van der Waals radii, covalent radius, atomic radius, van der Waals radii and covalent radius. Overall, the way we kind of define atomic radius is just an average of the various types of ways that we can measure the radius of an atom, okay? So what are we trying to say when we're talking about radius? We're just kind of trying to get an idea of overall size, right? The radius is a good proxy for just how big an atom is. So we're looking at the trends in atomic size overall with respect to the periodic table. Okay, so what do we actually see, right? So for main group, that's what we're going to deal with first. Remember that main group are the first 2 columns and then the last 6 columns, right? So this is filling of the s orbitals, s over here, and then filling of the p orbitals over here. When we look at trends in the atomic radius or the atomic size for the main group elements, as we go from top to bottom, so we'll stop here, we'll start here at the top, as we go from top to bottom, overall what we will see with respect to atomic radius is something that would be kind of predictable, right? We'll see an increase in atomic radius, right? So that makes sense. As we put more and more and more electrons, which is what we're doing as we go from top to bottom, we get more and more orbitals, so the thing is going to get bigger and bigger and bigger, okay? So elements, as we move from top to bottom in the periodic table, we will see an increase in atomic radius, okay? Now, utilizing that exact same kind of logic, you would expect as we moved from left to the right on the periodic table, you would probably try to see, okay, well, we're also still adding electrons as we move from left to right, so we'll probably see an increase as well. But that would actually be incorrect. What we see as we move from left to right is an overall decrease in the atomic radius or the atomic size of the individual atoms, okay? So as we move from top to bottom, we see an increase. As we move from left to right, we see a decrease, which is kind of counterintuitive. Okay, so to try to explain why we see a decrease in atomic radius as we move from left to right across the periodic table, we're going to bring into account this idea or this concept that we introduced last chapter, which is called shielding, right? And so to kind of just reintroduce you to shielding, I'm going to invoke lithium kind of as our little model of shielding, right? So lithium, if we look in the periodic table, has 3 protons in the nucleus. That's not a T. I don't know why I drew that as a T. That is a plus. Okay, it has 3 protons in the nucleus, and its electron configuration, if we look, is 1s2, 2s1. Okay, so now what is this concept of shielding? So lithium, with respect to its nucleus, it has 3 protons, so that means it has a +3 positive charge in the nucleus. It's got 2 electrons in that lower filled energy level, right? So this is the 1s2 energy level, and then it's got 1 electron left on the outside. That's essentially going to be determining the overall size of our atom, right? So remember that these electrons we just mentioned in the outermost principal energy level are the valence electrons, and then these guys that are in these lower filled shells, these are our core electrons, okay? All right, so the big idea here is that the valence electrons is going to essentially determine how big our atom is. The stronger the attraction that they have for the nucleus, the tighter the pull the nucleus will exert on this valence electrons, and overall the smaller the size. So the more attraction, I should put that, more attraction this little outside valence electron feels for the nucleus, the smaller the atom. All right, because it's going to pull it closer, and overall it's going to be smaller in size because of that. Okay, so what are the various forces that are affecting the attraction for our little valence electrons for the nucleus? So this is where shielding comes into effect, right? So if we think of Coulomb's law, we know that a positive and a negative, that's an attractive force. That's going to lower potential energy, and it's going to be proportional to the magnitude of the overall charge. So our nucleus has a +3 charge, and our electron here has just a -1 charge, right? So if they were just by themselves, this would have an overall +3 pull towards the nucleus, right? But this guy, our valence electron, is also being repulsed by our 2 core electrons, right? And so this is a minus and a minus, and a minus and a minus here. And so because of the presence of these 2 core electrons, they kind of reduce that pull by each individual one by 1. So overall, our little valence electron only feels a +1 pull towards the nucleus because of the presence of those core electrons. So if it was by itself, it would feel a +3. Because of the 2 core electrons, it only feels a +1 because it's being simultaneously repulsed by those 2 core electrons. This is pull towards nucleus. Okay, so that's kind of nice. Okay, so that's going to kind of define how we're going to be looking at these. We can actually quantify this pull towards the nucleus by something that is called effective nuclear charge. Okay, so how do we actually going to quantify this effective nuclear charge? So we have a nice little equation for it, right? So the effective nuclear charge, and this is essentially the part or the portion of the nuclear charge that our valence electrons actually feel, is given by Z minus S, where Z is the actual nuclear charge. This is the number of protons in the nucleus. And then S, we're subtracting away from that the number of core electrons. Okay, so for lithium, the effective nuclear charge would have been, as we just kind of demonstrated, the nuclear charge, which was a +3, minus the number of core electrons, which was 2, which gives us a +1 overall, okay? And again, this +1 is how much of a pull that outer valence electron feels for the nucleus. Okay, so now we can kind of quantify this and we don't have to think about all these various factors that go into play. Okay, so to kind of explain how this concept of shielding and effective nuclear charge are again going to explain the trend that we see in atomic radius, I'm going to compare lithium, which I've essentially redrawn, to beryllium, who's just to the right of lithium. Okay, so for lithium, we know we have 3 protons, so that's a +3 pull towards the nucleus. We have 2 core electrons, and we have 1 valence electron, which is this guy who's out here. And we also know that this valence electron feels an effective nuclear charge, is the effective of a +1, right? So he only feels a +1 pull towards the nucleus because he's being repulsed by these guys, okay? All right, so now we can do the same thing for beryllium. So beryllium has 4 protons in the nucleus, and it has an electron configuration of 1s2, 2s2, okay? All right, so if we draw the same thing for beryllium, so we'll draw the nucleus here, so +4 towards the nucleus, and then we'll draw the core electrons, so we've got an electron, and now we'll draw the valence electrons for beryllium. We've got an electron and an electron, okay? What's really important to note is, again, it's going to be the valence electrons that are going to determine our atomic radius, our overall size of the atom, okay? Another important thing to note is that outer electrons, or valence electrons, do not shield each other, right? They don't feel any effect with respect to each other. It's only core electrons that shield these outer valence electrons, okay? So we can go ahead and calculate the effective nuclear charge for beryllium. So effective nuclear charge would be our nuclear charge, which is a +4, because there are 4 protons in the nucleus, minus the core electrons, which again are only these 1s2. So overall, these guys, these valence electrons on the outside, feel a +2 pull towards the nucleus. And the big thing that has changed with respect to lithium is the fact that as we move from left to right with respect to the periodic table, the core electrons stay the exact same, right? Because again, as we keep moving, as we go from beryllium to aluminum, aluminum will have 1s2, 2s2, 2p1. These are our valence, these are our core, okay? Core electron remain the exact same as we move from left to right. What changes, though, is the number of protons in the nucleus, right? So the nuclear charge changes overall as we move from left to right. It increases, and so because of that, we see a larger effective nuclear charge going from left to right across the periodic table. That effective nuclear charge increases, which pulls these outer valence electrons closer to the nucleus, which overall decreases the size of the atom, okay? So again, top to bottom, we see an increase because all we're doing there is just adding electrons, adding orbitals. As we move from left to right, though, we see a decrease because the core electrons remain the same as we move from left to right. The only thing that changes is the nuclear charge, and so because of that, the effective nuclear charge increases as we move from left to right, which pulls those outer valence electrons in tighter, which decreases the radius, okay? So this is an editorial note at the end. I had incorrectly stated that aluminum was next in terms of moving from left to right across the periodic table. That is incorrect, and I'm glad I caught that, but I'm not going to re-record this because I refuse to. This is boron. This is not aluminum, okay? But same exact concept, and I'm trying to prove the same exact point, okay? Okay, so this kind of just recapitulates what I just said, or just restates it in words. You can read this. Again, it's a nice little summary slide. All right, so what about, that was main group. So we mentioned that earlier. We probably have lost it in the shuffle of me trying to explain these trends. But that trend that I just showed you was for main group elements, right? So what about our transition metals, our D block metals that are right in the middle, okay? So what we find with respect to the transition metals, so let me go ahead and write an electron configuration for a transition metal. So let's say that we're going to write the electron configuration for iron. Okay, so iron is argon. I'm just going to go ahead and abbreviate this. So noble gas, and then we have 4s2 3d6. Okay, this is the electron configuration for iron, which is a transition metal. Okay, and what I'm looking at here again is what is the trend in atomic radius for the transition metals. All right, so with respect, I'm going to try to demonstrate this with respect to iron. All right, so if we keep the exact same concept, right, where it's going to be the valence electrons that, and the pool of the nucleus for the valence electrons that kind of determine the overall size of the atom. Who are the valence electrons for iron? So hopefully, if you guys remember, the valence electrons are the electrons in the outermost principal energy level, right? And so with respect to the transition metals, we fill the 4s and the 5s first before we move on to the d's, which are at a lower principal quantum number, right? So these guys are the valence electrons. And as we move from left to right across the transition metals, they stay the same. We have filled these 4s orbital first, the 5s orbital, whichever. We filled the s orbitals first before we move to the d's. So as we move from left to right, the valence electrons remain the same. And so because of that, what we see for trends as we move from left to right is that the size overall remains the same as well. All right, so we don't see any type of change with respect to the atomic radius for the transition metals. So again, left to right across the transition series, we don't see a change. They kind of remain the same. As we move from top to bottom, though, we will see an increase. And again, this is going back to just the ideas that we presented with respect to the increase in moving from top to bottom overall. All right, we increase orbitals, we increase electrons, so the thing is going to get bigger overall. Okay, so here's a question. So for this one, this would be very similar to what type of question you'd see on an exam, right? Just on the basis of trends, I want you to tell me which is the larger atom in the pair that I present you, right? So for A, I want to know who is bigger, nitrogen or fluorine. And then in B, fluorine and selenium. C, aluminum or germanium. D, aluminum or nitrogen. And so for these guys, there could be the possibility of saying, oh, this one's bigger than this one. You could also be in a position where maybe you couldn't tell on the basis of periodic trends. And so maybe you would come into a situation like that in one of these answers. So go ahead and try this and then come back for the answer. Okay, so just as a reminder with respect to our trend in atomic radius, so as we move from top to bottom in the periodic table, we are going to increase in atomic radius, and as we move from left to right in the periodic table, we are going to decrease our atomic radius, okay? Now, important thing to have here would be a periodic table. That is what you will be given on the exam, and so it would be smart to try to predict these just looking at the periodic table. All right, so for A, we have nitrogen versus fluorine. So nitrogen, these guys are both in row 2, in period 2. So nitrogen is here, and then fluorine is to the right of it, right? So if we are in the same exact row, which is what we are here, fluorine is farther to the right, meaning it's smaller. So for this guy, nitrogen would be the larger atom. In B, we have fluorine versus selenium. So then oxygen goes here in the periodic table, sulfur goes right below it, and then selenium is in the exact same column, 2 rows down from oxygen. Again, if we're asking about fluorine versus selenium, we are increasing as we go from top to bottom, and then fluorine is to the right of selenium anyways, so selenium would be the larger of the pair. Okay, so then we're going to deal with aluminum. So it's nitrogen, carbon, boron. Aluminum is right here, and this is silicon, phosphorus. This is gallium, and this is germanium, okay? Germanium, and there is an arsenic right here, but we're ignoring that anyways. Okay, so the question here for C is aluminum versus germanium, all right? And so aluminum is to the left of germanium, meaning that in theory it would be slightly bigger, or it would be bigger than silicon, but then as we go to a step down, we see an increase as well. So this is one of those where it's like, oh, we step one to the right and one down. It would be hard to tell on the basis of trends for this one. So this one I would say can't tell, because again, the two steps that we make are kind of counter opposing one another. If we make one step to the right, we're going to decrease. If we make one step down, we're going to increase. So it's kind of hard to tell for this one, so I'd say can't tell. And then last we have aluminum versus nitrogen. So aluminum's bigger already because we're increasing from top to bottom. Nitrogen is smaller anyways because it's two places to the right. So the larger atom here would be aluminum. Okay, so again, using trends, you should be able to predict these with the help and the aid of the periodic table. Okay, so now we're going to start talking. We just talked about the periodic trends and atomic radius. We're now going to start talking about what happens with respect to ions. Okay, so we're going to, again, differentiate between main group ions and then transition metal ions, because they tend to behave differently. Okay, so as a reminder, what are ions? So ions are atoms that have either lost or gained an electron, or multiple electrons, right? So we're forming charged particles here. That's what ions are. We have two different types of ions. We have cations and anions. And cations are positively charged, anions are negatively charged. This is because these guys have lost electrons and these guys have gained. Okay, so that's what we already knew. We already knew all of that stuff, right? Now we're going to try to explain the formation of ions on the basis of quantum mechanics, right? So if we're gaining electrons, we're losing electrons, those are going to be coming from our quantum mechanical orbitals that we have developed. All right, so how do we know where these electrons are coming from? So for main group cations, what we are going to do is we are going to remove electrons in the reverse order of how we put them in, right? So for example, aluminum, as we fill our little orbitals with respect to our electron configuration, the last electrons that we put in, which for aluminum would be the 3s2, 3p1, when we remove 3 electrons to form our aluminum 3+ cation, we're going to remove them from the last orbitals that we put them in. So they're going to come from this guy, and they're going to come from this guy. So the aluminum 3+ cation would have the electron configuration of this, which ends up being the noble gas configuration of neon, okay? All right, so that's okay. That makes sense. Kind of the same thing that we've been doing thus far. The difference, so again, we're going to remove them in the reverse order that we put them in for main group. Now, the difference comes in with respect to transition metals, okay? So in transition metals, what's going to happen is instead of removing them in the reverse order of how we put them in to form cations and transition metals, we're going to remove them from the valence shell first, right? So for example, iron, so I already drew out iron a little bit ago. It had an electron configuration of argon, and then 4s2, 3d6, okay? So now, if we are going to form our iron 2+ cation, instead of removing them in the reverse order of where we put them in, which would come from the Ds, we are instead going to remove them from their valence electron, or their valence shell first. So the first electrons that would come out would be the s electrons, right? So for iron 2+, we would be left with argon 4s0, 3d6. Okay, and so again, this is different than with respect to all of the main group metals that we could form cations with. Once we have removed them from their valence shell, then we'll start to remove them in the reverse order of how we put them in. So iron can also form a 3+ ion, meaning it loses 3 electrons. And so the electron configuration for that would be 4s0, because again, I've already removed all of those electrons, and now 3d5. So now we're going to start removing them in the reverse order of how we put them in. Okay? Okay. So that's the big difference, main group versus transition metal. Okay, so this kind of discussion regarding transition metals and their cations that they form leads us into 2 new vocabulary words. Now, we've kind of already talked about it. I don't know why we wait to tell you about these guys at this point in time. But remember that the electron, right? The electron is a spinning charged particle, right? And so the spinning charged particle component of it produces a magnetic field. And that's where we got the spin quantum number, the m sub s of +1/2 and -1/2, or what we called spin up versus spin down. So if we have electrons and they are paired with spin up and spin down, this essentially cancels that net magnetic moment that each individual electron has, right? If we, on the other hand, have electrons that are unpaired, so unpaired electrons, the atom that contains these unpaired electrons will have a net magnetic moment, and so therefore it will be either attracted or it will interact with the magnetic field. I think that's a better way to put it, okay? So we had talked about that before. Paired electrons have electrons in orbitals with spin up and spin down. They're paired. Unpaired electrons are just sitting there by themselves in their individual orbitals. So these 2 different scenarios have different names. So if you have an unpaired electron overall in an orbital, that atom is called paramagnetic. So paramagnetic things have unpaired electrons in orbitals, and these guys will interact with the magnetic field. If everybody, all the electrons are paired, then we call those types of atoms diamagnetic. So paramagnetic versus diamagnetic. Zinc is a good example of a diamagnetic atom, right? And so instead of being attracted, they are actually slightly repelled to magnetic field. They don't really interact with the magnetic field because, again, overall, all of their spins are paired and they do not have a net magnetic moment. Okay, so just 2 more vocabulary words to be aware of. Okay, so here's a question where you guys could be applying this. So I want you to write out the valence, I want you to write out the electron configuration for each ion that I've put A, B, and C. Then I want you to draw the orbital diagram and tell me whether the atom or the ion is paramagnetic or diamagnetic. And so when I mean orbital diagram here, I only want you to write the orbital diagram for the valence electrons. So for some of these, it can be gigantic hassle to write the complete orbital diagram. So just focus on the orbital diagram for the valence electrons. And then you should write out, well, I mean, you can use the abbreviated electron configuration, but you should write out the full electron configuration. All right, so go ahead, try that, and come back for the answer. Okay, so cobalt is number 1. We're going to write out the electron configuration for the cobalt 2+ ion. So really quickly, I'm going to go ahead and just write out the electron configuration for cobalt by itself. So no ion formation, just neutral cobalt. So cobalt by itself is argon, and then 4s2, 3d7. All right, so if we're going to form the 2+ cation, we are going to lose 2 electrons. So for the transition metals, those electrons are going to come from the valence shell. So for cobalt 2+, that's going to give us argon 4s0, because the valence shell is the 4s orbitals, and then 3d7. If I drew out the orbital diagram, I guess I shouldn't say valence electrons, that's kind of, misleading. So whatever these guys are here, I'm going to go ahead and draw it for 4s, and then my 5 3ds, 2, 3, it's close enough. Okay, so here's my 3d orbitals. So I have nothing in the s orbitals in the ion. And then I have 7 electrons. So using Hund's rule, I'd put them in singly first. And then I'd go back and pair their spins. So it's 1, 2, 3, 4, 5, 6, 7. So in these last 3 orbitals, these guys are all unpaired. And since I have unpaired electrons, then this is paramagnetic. Okay, unpaired electrons gives you paramagnetic atoms. This would be attracted, or it would be, or interact with a magnetic field if we applied it. All right, so B, we're actually not forming a cation. I didn't really mention this before. We're forming an anion, so we're gaining electrons. So for nitrogen by itself, electron configuration is 1s2, 2s2, 2p3. If we are forming the 3 plus or 3 minus anion, we're going to gain 3 electrons. And so where those going to go? Well, they're just going to fill this unfilled shell, right? So they're just going to go into the p orbitals to fill that and form 1s2, 2s2, 2p6, which is also the electron configuration for the nearest noble gas, neon. Okay, if we're going to draw out the orbital diagram for the valence electrons, we would have our little 2s, and then we would have our 3 2p's. And for nitrogen, 3 minus, this would be completely filled. So there are no unpaired electrons here. Everything is diamagnetic. Okay, and so then last guy, calcium. Calcium is main group. We're forming the calcium 2 plus cation. So calcium by itself is argon, and then it is 4s2. So for main group, we just take them out in reverse order of how we put them in. So we're going to lose 2 electrons here to form the 2 plus cation. We're going to be left with calcium 2 plus, which is just argon. And you don't even have to draw this out. Argon, the valence electrons are 3s2, 3p, 3p6. Everything is going to be filled. So this would also be diamagnetic. Might as well. Cool. All right. Okay, so now that we can make cations and anions, we're going to now look at the trends in atomic radius for ions comparatively to their neutral counterparts, right? And we're going to kind of explain this using sodium as the model. Okay, so if we wrote out the electron configuration for sodium, we would write out neon 3s1, right? I'm going to go ahead and write out the entire electron configuration here. This is 1s2, 2s2, 2p6, 3s1. Okay, now if we form the sodium plus 1 ion, the sodium plus 1 cation, we're going to remove an electron. Again, it's going to come from whoever we put it in last. So the new electron configuration for the plus 1 cation of sodium is just the electron configuration of neon. So 2s2, or 1s2, 2s2, 2p6. Okay? All right, so now the question is, who is bigger or who is smaller? Is there any difference between the neutral atom and the cation that forms from it after losing an electron with respect to atomic size? So the big idea here is there any difference with respect to atomic radius? Okay. All right, so we're going to go back to this concept of effective nuclear charge to help explain this, right? So for example, if we look at sodium, right, so sodium's going to have 11 protons in the nucleus. So it's going to have a plus 11 pull towards the nucleus. It's got 1s2, the 2s, and then for Sodium by itself, it's got this one lone electron hanging out here. So if we draw, this is 1, 2, 3, 4, 5, 6, 7, 8. Okay? All right, so question is, for sodium by itself, what pull towards the nucleus does this lone little valence electron feel, given that it's being shielded by all of these core electrons? So if we calculated the nuclear charge for sodium, neutral sodium, we would take the nuclear charge and then minus the core electrons. So for sodium, the nuclear charge is plus 11. The core electrons here are all of these guys, right? So 2, 4, 6, so minus 10 gives us a positive 1, okay? So this guy from neutral sodium only feels a plus 1, so a plus 1 pull towards the nucleus, okay? So that makes it whatever size it is based on that. Now, let's look at the cation that we have formed by removing that one valence electron, right? And let's consider how much of a pull it has towards the nucleus for that. Okay, so if we have our sodium plus 1, so same thing, if we want to consider the effective nuclear charge here, we would take our nuclear charge minus our core electrons. So this would still be plus 11 because it still has 11 protons in the nucleus, but now who are the core electrons? All right, so we look at the electron configuration for sodium plus 1. The core electrons are now just these guys. These are our valence electrons. These are the electrons in the outermost principal energy level. And so for core electrons, we only have 2 here, right? And so because of that, those valence electrons for the sodium plus 1 will feel a plus 9 pull towards the nucleus, which means if we've got these guys, and we've got these guys, and these guys, who are now our new valence electrons, all 8 of these guys, they don't shield each other, 1, 2, 3, 4, 5, 6, 7, 8, but they feel a plus 9 pull towards the nucleus, which means that they're going to be pulled towards the nucleus much more comparatively than the neutral atom, which means that the atomic radius is going to be smaller. Because again, effective nuclear charge, we've changed the number of core electrons at this point in time when we've lost that one valence electron. And so now we're pulled much tighter towards the nucleus. That's going to give us a smaller overall atom. So in general, that's going to follow for main group pretty much for everyone, right? Cations, so positively charged ions, are going to be much smaller than their corresponding neutral atoms, okay? Okay, so we can even see that. We can compare lots of different atoms. So note, we give you the atomic radius for the neutral guy, and then we give you the atomic radius for the positive one cation, and the cations, or the whatever charge they are, doesn't really matter. The cations are going to be much, much, much smaller than the neutral corresponding atom. And that's a trend that you should know. All right, so what about anions, right? So anions are gaining electrons, so just remember that. And with respect to anions, we're not going to go into the great detail that we do for the cations to try to explain it. Just note that if you add electrons to something, that's going to increase repulsion overall, right? And so by adding electrons to form these anions, we're going to increase repulsion, which is overall going to increase the size. So no great explanation with respect to this. We're just going to see an increase in radius, an increase in size due to just increased repulsion by adding more electrons, okay? So because of that, big trend with respect to anions is that they are going to be larger than their corresponding neutral atoms. And again, we can show that. So when we compare our neutral atoms, so oxygen versus oxygen 2 minus, the neutral atom is smaller than the corresponding anion that is formed, okay? Again, that's a trend that you should be aware of. Okay, so I want you to try this question. So in each of these, I want you to tell me who is the larger atom. So for A, we have sulfur versus sulfur 2 minus, calcium versus calcium 2 plus, and then this is bromine minus versus krypton. So I'm going to go ahead and draw that. Bromine minus versus krypton. It's hard to see This is a minus. Okay, so in answering this, all you're going to do is apply what you've kind of hopefully just learned. So for A, we've got a comparison between a neutral atom and an anion. And so we just learned that anions are larger than their corresponding neutral atoms. So because of this, the larger atom here would be a sulfur 2 minus. We've also just learned that cations are smaller than their neutral atom. So because of that, the neutral calcium would be the larger atom in this pair. And this last one we have kind of, this is a little bit more of a questionable one. Not questionable, but it's going to require you to think a little bit more. So for bromine 1 minus and krypton, if we looked at the electron configuration for krypton, I'm only going to look at the abbreviated one. So this is going to be argon, and then argon 4s2 3d10 4p6. Okay, so that is the electron configuration for krypton. For bromine, in the neutral form, it would be argon 4s2 3d10 4p5, right? But if we have gained an electron, which is what has happened with respect to bromine, then that is going to make this 4p6, right? So both of these guys, bromine 1 minus and krypton, have the exact same electron configuration, right? So if we think about radius and the thing that's also going to affect radius, both of these guys, since they have the exact same electron configuration, have the same number of core electrons. Right, so if they have the same number of core electrons, how does krypton versus bromine 1 minus, how do they differ with respect to one another? So then the other thing that affects nuclear charge, or effective nuclear charge, that isn't the core electrons, is the overall nuclear charge, right? So who, between krypton and bromine, who has more protons in the nucleus? So hopefully you can see krypton has 36 protons in the nucleus, where bromine only has 35 protons in the nucleus. So if they have the same number of core electrons, but they differ in their nuclear charge, then krypton, because of that, is going to have a higher effective nuclear charge. It has more protons in the nucleus, which means it's going to pull in those valence electrons slightly tighter than bromine would. Okay, so the larger guy here, because of the difference in the nuclear charge, is bromine. They have the same number of core electrons, but they have different numbers of protons in the nucleus. The one with the more protons in the nucleus has a higher effective nuclear charge and a smaller radius. So these guys, bromine and krypton, this is something that we call isoelectronic. So isoelectronic atoms have the same number of electrons, right? And so frequently, like a favorite type of question for me to ask is, number one, to be able to identify an isoelectronic series, right? So if I give you, if I said bromine 1 minus krypton, and then I also said rubidium +1, as well as selenium 2 minus, all of these guys have the exact same electron configuration as krypton. They have the exact same number of electrons. So these guys are all isoelectronic with respect to one another. I also like to ask questions where I ask you to tell me who's got the bigger or smaller radius. Or if I wanted you to arrange them, could you arrange them from smallest to largest and vice versa? And again, it's using the exact same principle of effective nuclear charge. Who has more protons? They all have the same number of core electrons. And so because of that, who's going to be the bigger and the smaller ion? Okay, so hopefully that made some sense. And of course, I actually explained what I just stated in the previous slide and this slide. So again, with respect to isoelectronic series, these are going to be a series of atoms and ions that have the same number of electrons. The only way they differ is the number of protons in the nucleus. And so as we go from something like oxygen 2 minus, so oxygen 2 minus is the larger, and then as we increase the number of protons in the nucleus, again keeping the electrons the same, we get smaller and smaller and smaller. So just be aware of this trend and what it means to be isoelectronic. Okay, so the next trend, the next periodic trend that we're going to talk about is something called ionization energy. So this is defined as the energy required to remove an electron from an atom or ion. And so the way we define this, it's very specific, right? So we say this is going to be from an atom or ion in the gas state. That doesn't necessarily matter that much. But it is important to note that ionization energy is always positive, meaning that it always requires energy to take an electron away from something. So we can consider this like an endothermic process. Also important to note is that our valence electrons are the ones that are going to essentially be plucked off first, right? So the valence electrons are the most loosely held electrons. They're the farthest away from the nucleus, and so it's going to be the easiest to take one of those away. And when we do this with respect to ionization energy, it's always sequential, right? So let's say that we had something like calcium in the gas state, specifically in the gas state, and we wanted to form the calcium 2 plus ion. So this wouldn't happen all at the same time, right? We wouldn't take 2 electrons away from calcium to form calcium 2 plus. Instead, we would have our normal calcium losing 1 electron first. So this would be calcium plus 1 electron, and that would have its own ionization energy. That would be called ionization energy number 1. And then in the second step, we would take this calcium plus ion and take an electron away from it to form calcium 2 plus, and this would be called the second ionization energy, okay? So what we find is that the first electron, our first ionization energy, is always going to be the smallest. It's always going to be the easiest to remove, and then we're going to get larger and larger and larger in these successive ionization energies because it's always going to be harder and harder and harder to take an electron away. You can kind of imagine that in terms of charge buildup, right? As we take more electrons away, we're going to get more and more positive charge buildup, which is bad, it tends to be repulsive, etc. So these successive ionization energies are always going to get larger because it's always going to be harder to remove electrons as after the first one, essentially. Something like that. Okay, so what are our trends in these ionization energies? So what we find as we move from top to bottom, actually, I'm going to skip this one because, no, I'm not going to skip this, but I don't like this figure. I like this figure a little bit better. So what we find as we move from top to bottom with respect to the periodic table is we see an overall decrease in ionization energy. And so what's the idea behind that? So as we get bigger and bigger and bigger, which is what happens with respect to moving from top to bottom, those valence electrons, which are the ones that are going to be easiest to remove, easiest to pluck off, get farther and farther and farther away from the nucleus. And so because of that, they don't feel the nucleus and the pool that much anymore. And so it's easier to go in and take those electrons. So it requires less energy. All right, so then as we move from top to bottom, we see a decrease in ionization energy. As we move from left to right, we see in general an increase in ionization energy. And so again, this is kind of it's like a reverse trend, but it's similar to what we saw with respect to atomic radius, right? As we move from left to right, we increase the nuclear charge, which is going to increase the pool of those electrons in the valence shell. If they're attracted more to the nucleus, it's going to be harder to remove them. It's going to require more energy. Okay, so in general, what we see is this increase in ionization energy as we move from left to right. But there are a couple of little exceptions, which we didn't actually see in the atomic radius. So one of the exceptions is this little jump between beryllium and boron. So again, we should see an increase between these two, but we actually see a decrease. And then we also see a decrease in going from nitrogen to oxygen. And again, moving from left to right, we should see an increase. So how can we explain these little bumps that we see in our ionization energy, which I just stated? So yeah, I need to redo these slides. So again, yes, it increases except for here and here. So how can we explain that? So I'm going to explain this in terms of nitrogen and oxygen, and I'm going to do that by writing out the orbital diagrams for both nitrogen and oxygen. So nitrogen in the neutral form is going to have the orbital diagrams of this. So we have 3 electrons that go in the p orbital. Again, they go in singly first. And then for oxygen, the orbital diagram for its electrons would look something like this. So there are 4 electrons that go into the p orbitals. 3 of them go, and then we go back and pair the spin. Right, so now, what we're looking at with respect to ionization energy is taking an electron away from both of these guys, right? And so when we do that to nitrogen, notice I had briefly mentioned before that there is kind of a a stability to something that is half-filled, right? And so nitrogen by itself has a half-filled p shell, right? When we go in and we take an electron away from nitrogen, we disrupt that, all right? And so when we do that, we are left with this guy, which disrupts that half-filled p shell, which is kind of energetically bad. On the other hand, for oxygen, when we go in and take one electron away, we actually make it a nice half-filled p shell, right? Which is, again, energetically favorable. So because of that, this is why we see nitrogen have a larger first ionization energy comparatively to oxygen, even though the trend is kind of the reverse of that, right? Nitrogen is to the left of oxygen. Oxygen, in theory, should have a larger ionization energy, but it doesn't, because when we take an electron away, we form a half-filled shell, and we disrupt the half-filled shell for nitrogen. Okay, so go ahead and try these guys. So I want to know, on the basis of periodic trends, which element has the higher first ionization energy. So this would be aluminum or sulfur, arsenic and antimony, and then oxygen or chlorine. So go ahead and try these. And again, if it is possible, that's kind of the big keyword for some of these. I want to know who has the higher first ionization energy. Okay, so who's going to have the higher first ionization energy? Aluminum or sulfur? So we look at the periodic table. Aluminum is in row 3, right? So it's right at the beginning of the P block in row 3. And then sulfur, it goes aluminum, silicon, phosphorus, and then sulfur. Sulfur's in the same row, but it is 3 elements down. And so our trend here for ionization energy, in general, we see an increase as we move from left to right. So because of that, sulfur would have the higher first ionization energy. All right, so then we have arsenic versus antimony, which is these two. So arsenic lies right below phosphorus, and antimony lies right below it. So these guys are in the same column. As we go from top to bottom, we're going to see a decrease in ionization energy. And again, the cause of this, as we get bigger and bigger and bigger, it gets easier to remove an electron. So because of that, arsenic would have the higher first ionization energy. And then for this last one, we've got oxygen versus chlorine. And so oxygen is in the second row. It's right above sulfur. So we could put oxygen here. And then chlorine, so it's oxygen, fluorine. Chlorine's right below fluorine, right? So this is one of these ones where we should see an increase in one step to the right, but then we should see a decrease in moving down, right? So because of that, this would not be possible based on trends, right? I wouldn't expect you to be able to tell me who had the higher first ionization energy, because again, both of these movements, one to the right, that should be larger, but then one down should be smaller. They're both kind of like counteractive of one another. There is an answer to this, so you can look at ionization energies, but just on the basis of trends, it would not be possible to determine. Okay, so in the last little bit with respect to these ionization energies, so I told you previously that each electron being removed from an atom has its own ionization energy. And so we'll build up these successive ionization energies as we continuously remove electrons, right? So for example, for magnesium, this is going to be magnesium in the neutral form. Its first ionization energy is going to produce the magnesium +1 ion, and it has the smallest ionization energy because it's always easiest to remove the first electron. Then, for the second electron, magnesium +1 will lose an electron to make magnesium 2+, and this will have its own ionization energy, right? And so for this first ionization energy for magnesium, it's about 783 kilojoules per mole. And then for the second one, it's about 1450 kilojoules per mole. Okay, and so again, as we continuously do this, we're going to see this increase. If we then tried to remove the third electron from magnesium, we would take magnesium 2+, we would make magnesium 3+ an electron. This third ionization energy, even though we should expect it to be, an increase, we'll see a gigantic increase, right? So this ends up being about 7,730 kilojoules per mole, right? So these are pretty similar, they're kind of close to one another, but as we see this gigantic increase, this is a big indicator, and we can kind of demonstrate this with magnesium, that these guys were easy and we're nice and valence electrons, but when we jump into this one, we have reached our core electrons. And so these guys are going to cost us a lot more energy, respectively, because of that. And that makes sense for magnesium. So magnesium has an electron configuration of 1s2, 2s2, 2p6, 3s2. Right, and so the first electron would have come here. That wouldn't have been that hard, so we see this little 738. The second electron would have also come from its valence shell. So we do see an increase because, again, we expect that. But then when we get to the third electron, we see this gigantic increase, this tenfold increase, because now we're going to be dipping into the core electrons. And so sometimes there'll be questions that are very similar to that. Well, they'll have you predict what type of metal or what type of element we're dealing with given successive ionization energies. So for example, for sodium, if you had something that was nice and easy, and then the second one you see this tenfold increase, that would give you a big indicator that there is only one valence electron. Maybe let me write that a little bit better. A big indicator when we see this gigantic jump that there's only one valence electron, because when we get this big jump, that tells you that it's dipping into the core electrons. It's going to require a lot more energy. Same thing for magnesium. The first two being easy, the third being hard, tells you that there are two valence electrons. And then for aluminum, we see easy, big gigantic jump. That tells you that there are 3 valence electrons, right? And this goes on. Easy, big gigantic jump. That tells you again it's dipping into the core electrons. So sometimes what they'll do is they'll be like, oh, here's a set of successive ionization energies. I want you to identify what metal it is based on the fact that it's probably like a period 3 metal, and when you get to the 4th ionization energy, you get this gigantic jump. So you guys should be able to apply this ideally in the homework as well as on the exam. Okay, so I'm going to go ahead and finish this guy up because I'm tired of talking about periodic trends. So our last trend there's another one. second to last trend that we're going to talk about is something called electron affinity. So we had just talked about ionization energy. Ionization energy was losing electrons. Electron affinity, though, is defined as the opposite. It's actually gaining electrons, right? So what we have, or what happens when we gain electrons, is we actually release energy, right? And so ionization energies require energy. Electron affinities, or gaining electrons, are going to release energy, okay? Because this is essentially kind of like an exothermic process. So with respect to electron affinity, this again is just going to be how much energy is released whenever we gain an electron. And again, these are going to be successive as well. So what actual trends do we see with respect to electron affinity? So as we move from top to bottom, we see a decrease down a column. And generally, we see an increase across the period. So that means as we go from top to bottom, in general, we see a decrease in electron affinity. And as we go from left to right, in general, we see an increase in electron affinity. Again, notice that for some of these guys, this isn't the case. And so electron affinities really kind of start to be the ones where it's like, is this really a trend? Because they don't really all follow suit. And so because of that, I don't really like to ask questions about electron affinities, okay? But just note, what is it defining? It's defining the energy released when neutral atoms gain electrons. And in general, we see a decrease moving from top to bottom, an increase moving from left to right. And then the last trend, which again is something I don't really care all that much about, but it may be in the homework, is metallic character, okay? So just as a reminder, difference between metals versus nonmetals. So metals tend to lose electrons in chemical reactions. They are oxidized. They form cations. They're malleable. They're ductile. And they conduct heat and electricity well. Whereas nonmetals, we talked about them before, they tend to gain electrons in reactions that makes them form anions. And they are not very good conductors of heat or electricity, so therefore they tend to be insulators. Okay, so the last trend that we talk about is metallic character. This is just looking at how metal-like an element is, really. And the trend that we see in metallic character is we see a decrease from left to right across the periodic table, and we see an increase down a column. Okay, so that's fairly it. That's pretty much all you really need to know about metallic character. Again, we get a decrease as we move from left to right, and we get an increase as we move from top to bottom. This makes sense, right? So originally we had kind of defined this little dividing line, and we said these guys are nonmetals, and so these guys are metals. So as we move from left to right, as we go to the nonmetals, we should see metallic character decrease. That makes a lot of sense. As we move from top to bottom, we'll notice that this metallic character increases. Again, this has to do with things getting bigger and electrons being kind of freer to move around and conduct electricity or be lost in electrons or be lost in reactions, etc. more easily. So with metallic character, just kind of know decreases from left to right, increases from top to bottom. And that is it for chapter 7, right? So big takeaways, what I would really focus on is radius. I would focus on effective nuclear charge, right? And so explaining radius with respect to effective nuclear charge. I would focus on forming cations and anions and their trends with respect to radius. I would focus on ionization energies and the trends with respect to those, and that's probably it, right? And so with respect to this, I would also focus on what is an isoelectronic series, and then paramagnetism versus diamagnetism. But for the most part, I don't really care about metallic character, and I don't really care about electron affinities because, again, they bore me, okay? Okay, so that is it. Have a good weekend, and I'll see you on Tuesday.